building a house on Mars. You don't get this every day. And we have engineers with us, Jason Manes and Nicholas McGee. Thank you so much. Now, you're both engineers. You are entering a contest that NASA has asked for people to give them 3D homes that may be a habitat on Mars. Is that correct?
Yeah.
All right, so how did you decide to get involved in this?
I mean, I'm just real passionate about space travel. I think that it's really important for us as a species, and it's just incredibly exciting to venture out into the solar system. And
so as a kid, did you read sci-fi stuff and you saw movies and that was what you loved, or not so much?
I guess, I mean, I really developed the passion for it in my college years, as I learned more about the universe and the solar system.
And let's leave this one and go to another one and see what happens, right?
Yeah, sure. Well, I'm really interested in pushing the boundaries, right? Like, I want to see how far we can go.
That's good. All right, and how did you come together? Because there's a team of how many working on this 3D habitat?
So we have a team of, let's see,
I think it's grown to 7.
Yeah, seven now.
Seven people.
And primarily, I mean, most of us have met, well, I met most of the team through Nick, actually, because Nick kind of just brings everyone together. Yeah, he kind of has that kind of personality.
Oh, I love that. So you're a leader.
Yeah, essentially, yeah. So we got brought together basically by Nick and through the makerspace, Mick Haven, and basically he explained the project to us, and we kind of all felt passionate about it at that point. And obviously Mars is a really hot topic right now. It's in the news a lot for many reasons, through Elon Musk and various other...
pushing the boundaries.
Exactly, right, yeah.
So before we talk further, I just want to show a little video about what this competition is all about.
If we can recycle on Earth, why can't we recycle in space? Astronauts need to recycle as much as they can if they want to survive on Mars. So wouldn't it be cool if we could take some of the materials the astronauts aren't using and recycle them to build 3D printed habitats where astronauts can live and work? Pretty cool, right? We want your help to make this dream a reality. Help us turn this into this, and we'll turn your idea into this. Think you can solve this challenge? Show NASA Centennial Challenges you've got what it takes, and help us take the next giant leap in space recycling.
All right, so that kind of gives you a bird's eye view of what's going on. In front of us is what?
So we've got a few different materials here. This one is an unsorted Martian soil simulant.
What's it made out of?
So it's primarily basalt, silicon dioxide, different iron oxide.
Iron oxide as well, yeah. That's what the bread comes from.
And is it, can you set something in, will it stay, or does it move around like sand?
It moves around like sand. It's pretty dusty. So actually this is a refined version that kind of more accurately depicts the particle size that'll be blowing around on Mars.
And then what is this?
This one's a combination of the dust, the Martian dust, as well as a polyethylene powder.
So the challenge is to take what's there and make houses on Mars for astronauts, habitats. So NASA wants you to come up with a 3D printout, which is what you've been doing. And everybody, all the schools that are involved in this, or all the groups that are involved, how many? 5 or so in the country, or more than that?
Much more than that. I know that they ended up with 18 submissions, but I think they started out with maybe around 70 teams. I don't exactly know.
Right.
I'm kind of deciphering the email list, but...
Who's your competition? I mean, are you able to see what everybody else is doing?
We've been able to see 3 videos that have been posted onto the Facebook group. So there's one team that is a joint between, I believe, an architecture firm and a construction firm, and then one is like Northwestern University. And I assume, Caterpillar has a team, and there's other corporations and universities.
But you're going to win, right?
Of course, yeah.
Yes, okay. So you get this project, and there's money at the end of the rainbow here. How much?
So in total, there's about $2.5 million of prize money, but that is split up between a bunch of different phases of the competition.
To help you build it, or you get to spend it freely?
So the goal is to have that reinforce the technology that we're developing. So the initial phase, if we win some money in the first phase, we can fund the future phases of the competition.
So NASA comes up with a plan that they want these teams to emulate and to make in 3D form. How do the teams differ? I mean, how is it that yours is better than another team? That you do what with what you're building?
So I think the primary difference between ours is the method of manufacture. So a lot of people, we think, are using a concrete type 3D printed material, whereas we're looking at using this basalt fiber to be fed into a laser to be melted and deposited. So it's a little bit...
You realize this is Greek to me, so let's take it slow. What?
Sure.
So what is that made out of? What is that?
So this right here is rock. It's basically melted lava drawn through a small orifice to make a fiber. So it's a continuous fiber, just like carbon fiber or glass fiber you'd find in a boat hull or on an airplane.
Okay, all right.
And so we anticipate using this to feed into a laser beam, and then as that beam melts the material, it deposits it onto a surface. So these items here is what would be produced with that method.
What? And so that's made out of all of that.
Correct.
It's a rock.
It's a rock.
lava.
Yeah, it's like hot lava, just in a fused deposition method.
All right, Jason, weigh in any time here. Now, I saw the plans that NASA put out, and that's in another video. So these are all similar. It's just the types of material you guys are trying to come up with that differ?
So I guess the thing that's different between some of the teams are some teams have a more approach that requires bringing a lot more material from Earth. Our approach was to utilize as much material from Mars as possible. So that's why we're using basalt fiber and the regolith itself. The basalt fiber can be easily found on Mars. It's actually like pre-batched, I guess I'll say, in the rocks that are, like there's a lot of rock in the regolith mixed in, and it's kind of pre-batched already in similar form to this. Basically what you do is take those rocks and melt it and draw it out in a fiber, and you get this sort of material. Then we can utilize that for many applications within this structure as far as the supports and actually reinforcing the tiles themselves.
What else is found on Mars that you're going to use in a habitat?
So the yeah, there's not very
Not much,
yeah.
right? That we know of,
yeah,
right?
it's a very small list. So the regolith itself is obviously there, and the reason we're using polyethylene in the mixture is because that can be actually extracted from the atmosphere, from the CO2-rich atmosphere, and basically you take the CO2 and convert it into polyethylene, which is it's a well-known process. It's a little bit energy intensive, but it allows you to basically make polyethylene from the air.
Let's say you guys win. How do we get this habitat up to Mars? We don't build it there.
That's the
We
goal.
do build it there,
Yeah,
okay.
autonomous development. So we're looking to be able to send some robots up there and autonomously create this environment. That's actually one of the critical judging criteria for the future levels of development.
This
of
is
the competition.
mind-boggling to me, just mind-boggling.
Right.
All right, so here, let's show the 5 pictures that we have of what this little habitat's going to look like, and we'll just go through this. This is the house, correct, or one of the,
Sure.
let's call it a living room. What
Yeah.
is that?
The primary volume or the main sphere, I don't know.
And how big is that?
So that is about 27 feet in diameter.
Okay, so
On the inside.
And it will fit how many people?
So the goal was to develop a habitat to house 4 people for a year.
Okay. All right. Let's go to the next picture, which is, now there's a little tiny village. So you've got the main structure, and then what are the 2 outcroppings?
So the main structure, I guess, is the main living area, is what we'll say.
Yeah.
And one of the outcroppings is more of the I'll say the relaxation area. It's designed so basically you can, most of the primary work would be done in the large sphere, and the smaller one on the right side there would be where people can go to relax after they're done working.
Okay. And you can see a little astronaut there on the left.
Exactly. And the one on the left is actually would be more of an airlock, so you can get in and out of the facility or the structure to get to the surface of Mars, or like the rover, for example.
Because you got to have a car up there,
Exactly,
of course.
right.
All right, let's go to the next photo. So there you can kind of see a size. That's an astronaut. Next one. All right, some more. That's going to get into the interior, and we'll do that in a second. And then the final photo. All right, so there you can kind of see size. All right, so let's come back to the model. This is the main home, if you will. What's inside here?
Okay, so inside the main sphere, you'll have a secondary printing of this basalt type material to fabricate the structural pieces of it. So on this level here, you can see where these support panels or these floor panels would be inserted to provide the the work surfaces or the
So it's a
living
two-story
surfaces.
situation?
Correct. Internally, it's a two-story situation. So if you look here, you can see this stairwell that's built into the habitat, and that's to make the most of the volume interior, and also to kind of encourage some vertical movement. Because Mars doesn't have the same gravity that we do here on Earth, you kind of lose a lot of your muscle mass, and so getting the astronauts active and moving around inside the habitat is a plus.
It's crucial.
Yeah.
All right, these look so funny to me. Why is it that we want a habitat or a house on Mars to sit off the ground? What's the purpose of that?
Primarily the fabrication requirements. So one of the reasons why it's a sphere like this is because you need to retain pressure. So here on Earth, at sea level, we have about 14 psi of pressure on our bodies, like holding our organs in place. On Mars, they have about 8% of that, I think.
Yeah, okay.
I forget exactly the number.
That's okay, you got a lot going on.
Yeah, well, I'm on TV, so I'm a little nervous.
No, not to worry.
And so it's really challenging to create a structure that can retain that pressure with any resistance to impact from meteorites. Or
Yeah, I mean, is there a lot of stuff coming at this? And is this reinforced stuff? This is the exterior, right? Or is this the interior?
So that would be the exterior. It's one of these smaller volumes
Okay.
here, essentially. That's just a portion of it.
Okay.
The tiles themselves are actually reinforced with that same basalt fiber we were talking about earlier.
Right, so this can take a meteor hit.
It's the idea, yeah. It'd be, it's similar to like a composite you would see in like a fiberglass or carbon fiber or something like that, is the idea.
And what is the black, is that part of the outside or the inside?
Sure. So this is actually just the upper portion of the hab,
Right.
And it's in two pieces here. These were prototypes during the printing process, so we were just experimenting with different methods to produce the 3D model. But on Mars, they'd be produced singularly in these tile formats, and when they get assembled into the unit, they'll get welded along the seams here to retain the pressure, and then they'll get reinforced with like a binding clip to hold the panel in place and to hold that tension.
How many people know that this group, 5 or 7 of you, is working on a habitat on Mars?
I mean, we try to get as much publicity as we can via Instagram, things like that, but I would say not too many, really.
Well, now they're going to
Hopefully,
know
yeah,
about it.
that'd be excellent.
The next step is what? You're going to hear, as we tape this, it's June 5th. You're going to hear tomorrow, I guess, June 6th, about whether you advance to the next stage.
Yep, that'll be the day, yeah.
So you'll be calling me tomorrow.
We will.
All right, about what happens. Let's say you get to the next stage, then what?
Well, tomorrow we'll find out if we're in the top 10, and we'll have to do a video conference with the judging panel at Bradley University and with NASA, and go through this whole exercise again, I'm sure in much more rigor.
Yeah.
And hopefully if our idea holds water, we'll get some prize money, and it'll help fund us for the next level of the competition.
Let's say you win the whole thing. How long, I don't even know the answer to this question, how long before this maybe happens on Mars? Because you said depending on, it takes 3 to 9 months to get to Mars, and so in your lifetime, are we going to see this?
Oh, definitely.
Yeah.
Yeah. I mean, there's people talking about trips to Mars in 2024, and I think that this whole architecture will take a little bit longer to develop, but I think by 2030 we could have some first level prototypes going on Mars.
And you plan to be there, right?
Well,
That's part of it.
yeah, I'd love to be a part of it. Yeah, I'll do whatever I can to help push the bounds of human exploration.
All right, so both of you went to UConn,
Yes.
engineers. Is UConn, I mean, they must be fully aware that you guys are involved in this. Well, they are now.
Yeah, I guess, yeah.
Yeah,
I guess they're not, no.
No, they don't. I think eventually we'll be looking to partner with universities or companies in order to get access to some higher technology that we don't necessarily have access to now.
What are you going to eat on Mars? What are you going to, I mean, we know so little about, except for there's basically nothing there. I'm trying to wrap my head around how you're going to manufacture this in a room with a machine and build a house there.
Sure. I mean, for eating, I mean, depending on where you are, if you're the first people there, you're going to bring a lot of food with you. You ever, eaten one of those freeze-dried meals at REI or, those, I mean, that's going to be a primary constituent of the diet. So until we're able to develop an infrastructure where we can actually grow crops and develop production systems on Mars, we're going to be relying heavily on shipments from Earth.
So what are you guys learning about yourselves, about this, about Mars, about NASA as you work on this project?
I mean, the thing I learned, I guess, most about this is just how harsh the environment is on Mars. I mean, it's just looking at like, images of Mars and just looking at like pictures from the rover, things like that. It doesn't look as harsh as an environment it is. When you take into account all of the factors and concerns that would cause problems to the people living there, it kind of gives you an idea of how complicated the structure needs to be. That's one of the things I got out of it, I guess.
Yeah, I mean, there's insurmountable lessons that we've learned. I mean, from 3D printing and fabricating and manufacturing here on Earth to conceptual level development that, is on the cutting edge of technology.
NASA set up these plans and decided that this octagonal, if you will, shape works best. Would there be things that you would tell NASA that you're not so sure that would work and maybe it should be designed differently?
Sure. I mean, there are weaknesses to any of the designs, and we'll definitely discuss that when we work with NASA. I think it's important to identify those. We want to win, but we also are looking to push the boundaries and develop the technology. So we are aware of some weaknesses in the design here, and
like what?
Primarily the brittleness of this material. And so one of the things that we're working to do is refine the material that's going to feed it, so that we can eliminate inconsistencies or any anomalies in the material, so that we can get a more
robust material. So the basalt fiber, I guess what we're trying to get at here is the basalt fiber actually, when you print it into these structures, they actually tend to be kind of brittle, and they don't really, when you load them in tension, basically pulling them apart, they tend to have very poor mechanical properties, but in compression, they are much stronger. So the idea is we built the pillars here out of basalt, and they're all loaded in compression to maximize that property. So one of the weaknesses of this design would be the fact that you're using something that is relatively brittle.
Right, which might collapse, right?
Well, potentially.
Not really, though, because of the way it's loaded, but it's definitely a concern, yes.
So when the material is in this form, it actually has a very high tensile strength. And so that's why we utilize the fiber in this form for the tensile loading of the pressurized portion that I have.
Glass goes in here or something much harder for windows?
A glass. So we kept the glass to a minimum on the main sphere where the primary, where the astronauts will be spending most of their time because of radiation concerns and the amount of radiation that the glass lets through. But we thought it was important to have a connection with the outdoor, with the environment, and so that's why we kind of have this module here to allow the astronauts to connect with the environment without having to leave the...
How much daylight do they have in a day? I mean, what is it like there? Do you know?
So it's very similar to our planet. It's a 25-hour day approximately. So depending on
I
your
could use
latitude.
another hour. See, I should be on Mars. So it's similar.
Similar, yeah.
And temperatures.
Oh, that's one of the, as I was saying, harsh environment. That's one of the things that's pretty severe. It can get very cold. I believe -40, and even colder in some places.
-40°C.
Yeah, it's -40. Yeah.
Well.
What does this weigh? How many tons does this thing weigh? Do you know?
I'd have to reference our model, but I could tell you. I forget. The panels are on Earth are 8,000 pounds. On average, there's the difference between the hexagonal versus the pentagonal tiles, and then depending on what type of insert you have in there, the mechanical inserts or a window insert or a hatchway insert.
I'm just trying to picture astronauts. Is it weightlessness on Mars similar
About
to the moon?
40% of gravity.
Okay, so I'm trying to figure out working in that and building this structure.
Lower gravity will actually be helpful for the assembly process. So the components that you'll need to position the tiles while they're being assembled won't have to be as rigid, and they won't have as much energy demand as they would here on Earth.
I see. The two of you graduating from UConn, did you ever think you'd be working on this kind of a project, or did you think you'd be doing something else?
I mean, I didn't really know. I guess it's funny. I mean, I always envisioned something in the aerospace industry. So I guess it's
a great state for that.
Yeah, I guess it's kind of can be categorized as that. Not necessarily this exactly, though. No, I can't say that.
And how about you?
To be honest with you, I went to UConn hoping that I could find a way to work on, space applications. So, yeah.
Well, the best of luck to you both. I'm fascinated about what you're doing, and we hope that the state of Connecticut gets to boast that you guys, your team, is going to make the first house on Mars, because that would be really neat.
Yeah, it would be, absolutely.
Jason Manes and Nicholas McGee, thank you so much for being on.
Yeah, thank you.
Good luck.
Thanks.
Spend all night kissing and the bomb was right here, then who else is missing? Got a little sidetracked to find myself wishing to find the keys to the door, but it's also a metaphor. Need to keep locked in the grocery store, but mine just to save time. I'll skip right ahead to the last ride.